Hi X203. For this video, we're talking about composite relations. We've got a set of all mathematicians, and we've got a relation on that set where A relates to B if A and B have written a paper together. And we'd like to talk about the properties of R squared. So to start off, well, just what is R squared? We can go to our definition, and that's going to tell us that, well, A R squared C. What that means is that there's some B out there, some person B, where A relates to B and B relates to C. Or we can think about it a little bit more generally as, well, our relation R tells us we can get from A to B in a one step, and R squared is telling us that we can get from A to C in two steps with B in the middle. For this specific example, it's saying, well, A relates to C using R squared if A's written a paper with someone and then that someone's written a paper with C. So now that we have a little bit more of an intuitive understanding of what's going on with R squared, let's figure out its properties. So we're going to look at reflexive. Well, is this reflexive? Does every element relate to itself using R squared? And the tricky thing with this is, well, we're looking to see that every mathematician has written a paper with someone, and then that someone has written a paper with the original mathematician. But what if we find someone who's never written any papers? They couldn't possibly relate to anyone using R, and that means they can't relate to anyone, including themselves, using R squared. So that's the snag that's going to make this not reflexive. How about symmetric now? And so what we're looking for is we're looking to see, well, if A relates to C, then C should relate back to A. So let's see. If we have that A relates to C, well, what does that mean? That means we go to our definition, and then there's this person B, where A relates to B and B relates to C. What can we tell about that? Well, we're going to have to be a little clever and go back to our definition for R. And so we're going to see that, well, if A relates to B, A and B have written a paper together, then that means that B and A have written a paper. B relates back to A. And so we can use that. We can say, well, since B relates to C, then C relates to B. And since A relates to B, then B relates to A. And so we can combine that info. We're going to use our definition of R squared. And we can see that C relates to B and B relates to A means that C relates to A using R squared. So we've shown, using a combination of this definition of R squared and just the original relation, we've shown that this has to be symmetric. And this is a flow that you'll see a lot in composite relations questions. Now let's take a look at anti-symmetric. And so what we're looking to see is, well, if A relates to C using R squared, and C relates to A, do they have to be the same person? And an example I can give is, let's say we've got 3 math professors at U of M. And so Professor A has written a paper with Professor B. Professor B has written a paper with Professor C. And so we know from those two things, we can put them together and say, well, A relates to C using R squared. C relates to A using R squared. But A and C are not the same person. And so that's going to mean that this is not an anti-symmetric relation. Finally, let's take a look at transitive. So this one, we're looking to see, well, if A relates to C using R squared, and C relates to E, does that mean that A relates to E? Let's take a second and go back to our definition of R squared. So what this really means is for some B and D, it means that A relates to B and B relates to C, and then C relates to D and D relates to E. So A's written a paper with someone who's written a paper with someone else, who's written a paper with someone else, who's written a paper with E. And that seems like quite a bit of distance between A and E. There's absolutely no guarantees that A has actually written a paper with E. We can totally construct a situation where that doesn't happen. So this one is not transitive.